Hello everyone, thank you for signing in and watching my live stream. I'm Mr. Matt and this is Dr. Tot. You want a cookie, Dr. Tot? And thank you very much for signing in. Welcome to SAT ACT Prep. I'm so sorry that I wasn't able to stream Monday or Tuesday. We've been having some internet problems, but hopefully that's all resolved. If you see any problem or have any problem with the audio, please just let me know in the live chat function. But otherwise, welcome. It's good to see you guys all. Well, to be with you all again virtually. Today we're going to start the next section and I'm going to do a recording for session 2, so just look out for that and you can watch that at your convenience. But that way we'll be able to wrap up the section on Friday as we normally are scheduled to do with session 3. So that's my goal. I'm trying to make up all of these sessions, so I do understand. I appreciate everybody's understanding. But if you have any questions or concerns, then please just drop a comment below. You can hit me up at my social media accounts that are in the description. We're going to talk about interpreting remainders. So what's important, and that sounds really vague, but it comes up a lot in some SAT and ACT word problems where you have to investigate a particular pattern or repetitious segment. One question is that comes to mind pretty strongly is a machine that dispenses tokens or toys or gumballs or something in a particular order, and they ask you to figure out what color. They give you a sequence of colors like 3 blue, 4 white, 5 red, something like that. And they ask you to evaluate what the color of some really large sequence ending term is, like what color is the 10,000th gumball. And there's no way to have time in order to write out all those sequences 1,000 times to get up, or 10,000 times to get up to the 10,000th gumball. So you need some type of mathematical way of approaching the problem. And so we're going to look at that today. Let me go ahead and share my screen with you. And just remember, these are live sessions, so there is a little bit of a delay. If you have any trouble understanding me, or if you need me to scroll back up or anything like that, just let me know. But I first just want to give you an example of what I was talking about. Let's say that a token machine dispenses tokens in the following order. Let's say 3 blue, 2 yellow, and then 2 green. And then let's say that the pattern repeats, so on and so forth, starting with the first blue. And what if I asked you, what is the what is the color, or what color, what is the color of the 1,000th gumball, or token in this case? So what we can do here is we can identify the non-repetitious segment. So non-repetitious meaning non-repeating. So what is the unique sequence that keeps on repeating over and over again? We can think of it as we have 3 blue number positions. So we have the first 3 positions and they're all blue. Then the next 2 color positions would be yellow. And then the last 2 would be green. So notice in total, we have 7 unique color positions. So we can break this sequence down or simplify it. Instead of thinking of 1,000 color positions, we can break it down into, okay, well, it's just this color position or this sequence repeated over and over and over again. So if we take the 1,000 gumballs, or excuse me, tokens, I keep on saying gumballs, the 1,000 color positions that we're trying to analyze, and if we divide it by the 7 unique color positions, you're going to get a really nasty number. You're going to get 142.8571429. So let's talk about what this represents. If you're going from 0 gumballs all the way, or tokens, I'm sorry, from the 0th token all the way up to the 1000th token. Basically, what this number is saying is that this pattern you can think of as repeating itself over and over again. And so each one of these leaps represents a repetition of those 7 unique color positions. So what this quotient represents, and remember the quotient is just the answer to a division problem. So 142.8571429 is the quotient that I'm talking about. So this quotient represents 142 exact revolutions or repetitions of this segment and 0.871429 of a remainder into the next pattern or next unit of repetition. So, and that's really what we're interested in. They don't ask how many full patterns is this machine going to go through before hitting the 1000th gumball. If that were the case, then the answer would be 142. Be 142 complete revolutions or repetitions of this segment. But they ask us what color is the 1000th gumball. So I'm really interested in that remainder. That remainder tells me what percentage of the next 7 unique color positions does the 1000 total go into or land on. So we're really looking for how much we go into this last segment before falling at the 1000th gumball. So we're not going to be able to repeat a whole other segment of the 7 unique color positions. But we will be able to, but when we do hit the 1000th color position, that is representative, or that's the same thing, of 85.71429% into the next pattern repetition. So in order to solve, you're not really interested in this integer value of 142 because it's meaningless in this context. They don't ask us about how many times the pattern repeats. They ask us what the pattern lands on in the 100th term or the 1000th term. So in your calculator, do 1000 divided by 7. Then, without hitting anything else, because it has a repeating value, right? That decimal repeats infinitely. So in your calculator, without hitting anything else, just hit subtract 142, and that will allow your calculator to keep that exact decimal value. Then, so in your calculator, if you hit minus 142, you should have 0.8571429, or something like that, depending on how many values, how many digits your calculator rounds to, on your enter screen. Notice that decimals, percents, fractions, these are all the same thing. They're just different formats. So that decimal of 0.8571429, that is exactly the same thing as 85.17429% into the next repetition of 7 unique color positions. So that 0.857171429, that is what you need to multiply by your original divisor, by the number of original color units, color positions in this sequence. And if you do that right, if you leave that decimal in your calculator line and you just subtract away the 142, that'll capture that exact number. Even though it can only display so many digits, the calculator has that exact value in its computation. And so if you just do times 7, that will give you exactly 6. What this represents is that this color position is repeated 142 times exactly with a remainder of 6 color positions at the end. So what this tells us is that the 1000th token is going to be in the 6th color position. So the 1000th token in this problem would be green. Let me scroll back up here. If you have any questions, please let me know. I can make my camera a little bit smaller so you can see all of the information. So the main takeaway here, decimals, fractions, percents. These are all the same thing, and we're going to get really heavily into this in the next section. Right now we're doing foundational arithmetic, but we're going to get into fractions and percentages next. So we're going to get a lot more work with this. But fractions, decimals, percents, these are all the same thing. They're just different formats of representation. And if we have a unique color position, we can divide the total terms by the number of unique color positions or unique positions. It doesn't have to be color. It can be something else, some other characteristic. But you can divide the total number of terms by that the number of unique positions in the sequence, and then investigate the remainder. The remainder represents what you have left when you can't make a whole other repetition around that color sequence. So that will tell you what color position the last value lands on, which is what they're asking. If you have any questions, again, please let me know. Otherwise, this is the new format that I'm going to have for our lessons. They're going to be embedded in my virtual whiteboard here. At some point, I hope to have these all together to a point where they're available on the website, and these will be posted if you want to go back and look them up. Right now, our administrator is actually out sick, unfortunately, so I wasn't able to post it today, but if you're watching this recording, then if you look in the description, normally I'm going to try to have all of these resources available to you before class. I'll also try to post the Word version, so if you use assistive technology, some type of reader, that'll be accessible to you as well. So just to repeat kind of the gist of what I covered in that first example, when asked about the result of some pattern, sequence, or repetitious segment, you can use the decimal remainder to calculate a specific ending position or progress into the next interval depending on the context of the question. So these are highly subjective questions. The test makers have the ability to change just a little part of these questions and make it a totally different question. So these are not formulaic. These are things that you do need to make sure that you think through because it's not just a plug and play scenario. They can change the characteristics greatly by just changing a few words in these word problems. So just be careful, but we're going to go through several examples in different contexts today. Okay, I'm going to give you 5 minutes, and I'd like you to look at 1 and 2. Actually, I'm sorry. I'm going to give you 3 minutes, and I'd like you to look at 1 and 2. After the 3 minutes is up, then I'm going to give you some extra time to work through it, but I'm going to give you some hints after the 3 minutes. So I'll keep track of the time here in the upper right-hand corner, and I'll update it per minute. But I'll give you 3 minutes to start thinking about these two problems. I'm not expecting you to be able to solve them completely. If you can, then that's absolutely fabulous. If not, after the 3 minutes is up, I'm going to give you some hints, and then I'll give you an additional amount of time, probably 4 or 5 minutes. Okay, so 3 minutes, and then I'll give you some hints. And I do apologize. I'm going to pause the timer. I just want to make sure that I read the question. I always forget to do that. The first problem is a carnival vending machine dispenses toys in the following color pattern: 1 red, 3 blue, 5 green, 7 pink, and then repeats starting again with 1 red, etc. What color is the 300th toy? And number 2 says a carnival vending machine dispenses toys in the following color pattern: 2 red, 4 blue, 6 green, 8 pink, and then repeats starting with 1 red, etc. What color is the 300th toy? So I apologize, I just want to make sure that I read them before I give you the time. So I'll restart the timer 3 minutes and then I'll give you some hints. Okay, so number 1, a carnival vending machine dispenses toys in the following color pattern: 1 red, 3 blue, 5 green, 7 pink, and then repeats starting again with 1 red, etc. What is the 300th toy? Or what color is the 300th toy? So if we add up these unique color positions here, we have 1 red plus 3 blue plus 5 green plus 7 pink. So that's 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16. So we have 16 unique color positions. If you take 300 and you divide it by the 16 unique color positions, you're going to get a quotient with a decimal remainder. You're not interested in the whole number that is part of that quotient. That represents the total number of revolutions of this pattern of 1 red, 3 blue, 5 green, 7 pink. Instead, you're interested in the decimal remainder. The decimal remainder can be converted or thought of as a percentage a percentage of the progress into the next interval where you can't make a whole other revolution. So whatever that value is, you want to investigate that decimal, and you would multiply that decimal but without an integer value. So it's going to be 0 point something. It needs to be a value in between 0 and 1 to represent the percentage that it is. But whatever decimal it is, 0 point something, you're going to multiply that value by the original divisor, which was 16. You multiply that value by the original number of color positions in the problem, and that will give you the resulting color position of the last toy that you're interested in this case, the 300th toy. Same thing for number 2. We have 2 red plus 4 blue plus 6 green plus 8 pink. So that's a total of 20 color positions. So you do the same thing. You'd have 300 divided by 20 unique color positions. Now, I will give you a hint that if you have no remainder, that means that the last ending value goes exactly, the number of items in the non-repetitious segment goes exactly into the total number of items that you're evaluating. So if you have no remainder, that's indicative of it being the last item in the sequence, or the last color position in the sequence, because there's no other value that it's missing to do a full repetition of that pattern. Okay, so just a few hints. I'm going to give you 4 minutes to look over this. Actually, I'm going to make that 3 minutes. I'm going to give you 3 additional minutes, and then we'll review and go on to some other examples. Okay, so let's look at these two examples, and I see that somebody liked the stream. Thank you very much. If you find these videos helpful, feel free to subscribe and like the video. So thank you very much. I appreciate you. Number one, so if we take 300 total toys and divide it by the 16 unique color positions that we're investigating, then 300 divided by 16 is going to be 18.75. We're not interested in the 18. That means that there are 18 complete repetitions of this color pattern, but that's not what they ask about. They ask us what color does the 300th toy land on. So we're going to back out the integer value of 18 and investigate this remainder of 0.75. 0.75 is the same thing as 75% of another repetition. And how many units are in another repetition? Well, there's 16 unique color positions. So we're going to have 0.75 times 16, which is going to give you 12. So the 300th toy is in the 12th color position. 1 plus 3 is 4. 4 plus 5 is 9. 9 plus 7 is 16. So this 12th color position is one of the pink toys. So for number 1, the 300th toy is going to be pink. For number 2, we have 300 divided by 20. Now 300 is divisible by 20 exactly. It's 15.0. So this goes 15 times with a remainder of 0. That means that this lands exactly on the last color position. So this guy is also going to be pink. This one is the last pink toy in the entire sequence. If you have any questions, then please let me know. I'm going to give you 3 minutes. Please look at the next 2 problems. They are going to be a little bit different in their context, as I warned you. But after the 3 minutes is up, then I'll give you some hints, and we'll go through, I'll give you some hints, I'll give you some extra time, and then we'll go through a review. The first question says 453.2 pounds of polished marble stones are being divided into bags individually weighing 5.5 pounds. How many pounds of marble stones remain when there isn't enough to make another whole bag? And the second question, 614.55 pounds of polished marble stones are being divided into bags individually weighing 8.5 pounds. How many pounds of marble stones remain when there isn't enough to make another whole bag? So I'll give you 3 minutes, and then I'll give you some hints. Okay, let's look at 1 and 2, and thank you very much, Joshua, for your question. You are exactly right. So what we're going to do is we're going to take the total amount of pounds of whatever it is, so in this case it's marble stones, and we're going to divide it by the individual value of each of the individual weights of each of the bags it's being divided into, and then think of the decimal remainder of that quotient as a percentage progress into the next sequence, in this case into the next 5.5 pound of marbles. So take 400, oops, need my pen here. Take 453.2 and divide it by 5.5. We're going to get 82.4. So that means that we can make 82 full bags, 82 full 5.5 pound bags, with 0.4 remaining. 0.4 is the same thing as 40% of another bag. So I'll leave you with that. For number 2, we have 614.55 pounds being divided into bags, each weighing 8.5 pounds. So take 614.55 and divide it by 8.5. And we're going to get 72.3. Again, in the context of this question, the 72 really isn't relevant. That just represents 72 full bags that we can make. We're really interested in the 0.3 remainder. That represents 30% of another 8.5 pound bag. I'll give you another 3 minutes and then I'll give you the solutions. And actually, just for time's sake, I'm going to change that to 2 minutes. I hope that there's no protest. But 2 minutes, just because there's a whole bunch of problems that I'd like to give you exposure to. Okay, so for number 1, we're going to take 453.2 pounds, total pounds, and divide it by the individual unit of separation, or the amount of pounds in each bag, which is 5.5. That gives us 82.4. We're going to back out the 82 because they didn't ask us how many complete total bags we could make, which would be 82 in this case. They ask us how much were left over when we can't make another whole bag. So we're going to take the original divisor of 5.5 pounds per bag and multiply it by the 0.4 remainder when we can't make another whole bag. So 5.5 times 0.4 is going to be 2.2. So we're going to have 2.2 pounds left over when we can't make another whole bag. And for number 2, same type of deal. We're not interested in the 72 because that represents the 72 whole bags that we could make. Instead, we're going to take 8.5 pounds per bag and multiply it by the 30% remainder that we would have left over. 8.5 times 0.3 is 2.55. If you have any questions, please let me know. Otherwise, let's take a look at the next 2 problems. Now, I will warn you, the next 2 problems are tricky. There's a trick to it that you have to figure out that's a little bit different. But I don't want to spoil the result, and I want you to spend some time thinking about it because that's what you're going to be confronted with on the actual test. So, for example C's, we have 2 problems here. Number 1, Thanksgiving is always celebrated on the 4th Thursday in November. If Thanksgiving is on November 28th in 2013, then what date was Thanksgiving celebrated the following year? Note there are 365 days in a year. Number 2 says Labor Day is celebrated on the first Monday of every year. If the first Tuesday, notice how tricky that is, if the first Tuesday of September 2017 was September 5th, what date was Labor Day celebrated in 2018? And again, note that there are 365 days in a year. So these 2 problems are quite tricky, so I'm going to give you a little bit extra time. I'm going to give you 4 minutes to look over it, and then I'm going to give you some hints, and then I'll give you some more time to actually solve the problems completely. So 4 minutes, and then I'll give you some hints. And remember, the whole lesson today is investigating the remainder. So it might have something to do with the remainder. That would be a key. Okay, 4 minutes, then I'll give you some hints. Okay, so let's look at this. So the real trick here is that we need to investigate how the dates change from year to year. If we have 365 days in a year, and the days of the week are in a pattern sequence of 7 days in a non-repetitious unit, so you have Sunday through Saturday is a total of 7 days in a week. So if we take 365 days and divide it by 7 unique day positions, 365 divided by 7 is going to give you 52, a nasty number, 52.14857, so on and so forth. Again, if we investigate that remainder, subtract away the 52 because that represents 52 whole weeks in a year, but concentrate on this remainder. And I'm sorry, my broadcasting software said it disconnected, so I hope that everybody can still hear me. If not, then please let me know if you can hear me. If you can hear me. So if we investigate that remainder of 0.14857, that represents about 14.8% into the next week when we can't fit another week into the year. So if you multiply that by 7, you're going to get 1. So that means that there are 52 weeks, 1 day in a year. So every year, the dates shift forward by 1 day, unless you're talking about a leap year, in which case they would shift forward 2 days, 2 dates. So everything from 1 year to the next, every day is going to be 1 date ahead of the last year until they roll over into the next week. But for number 1, so I'm going to give you that. Now that you know everything changes for 1 date, I'm going to give you 3 additional minutes to look over 1 and 2, and then we'll go through the solution. Okay, so what we figured out is that there's a remainder of one whole day every year per week. If we divide a whole year into the number of weeks it represents, we have an extra day every year. So the dates shift forward. If we're not talking about a leap year, non-leap years, days shift forward one day. The dates shift forward one day. So if in 2013 Thanksgiving was celebrated on November 28th, then in the following year, in 2014, the days are going to shift forward one day. So you're going to have an extra day that year. So that's going to be celebrated now. That fourth Thursday will now be on the 29th. So however you wanted to write that out, November 29th, 2014. For number 2, Labor Day is celebrated on the first Monday of every year. If the first Tuesday of September 2017 was September 5th, what day was Labor Day celebrated on 2018? So if we think about in 2017, that first Tuesday was September 5th. So that means that first Monday was September 4th, and therefore the next the next year, all the dates are going to push forward one day. So in 2018, that Monday is actually going to be the 5th again. So we're going to have September 5th, 2018. If you have any questions, then please let me know. So now I'd like to get into some mixed sets. So you're going to see some more different versions of questions that we've covered today, just in different contexts. Remember that your vocab, sum represents the answer to an addition problem. Difference represents the answer to a subtraction problem. Product represents the answer to a multiplication problem. And quotient represents the answer to a division problem. So I have, there's 4 problems in set 1, but we'll take them 2 at a time. Question number 1 asks, what is the sum of the remainders of 47 and 58 when divided by 3? Hint is that you might want to use longhand division to evaluate that remainder, or you can use the same process as we have been, is by looking at the decimal remainder. And number 2 asks, Ryan is buying fruit at a local farmer's market that's priced at $3.65 per pound. If Ryan has $19.71 on a gift card, what percentage of another pound can be purchased, that should be purchased, when he cannot purchase another whole pound of fruit? So I'm going to give you 4 minutes, and then I'll give you some hints. Okay, so number 1, what's the sum of the remainders of 47 and 58 when divided by 3? So let's look what happens when we take 47 divided by 3 or 58 divided by 3. So 47 divided by 3 is going to be 15.6 bar. The bar just means that it repeats forever. So if I subtract away the 15, I'm going to get 0.6 bar, and then you multiply that by the original divisor of 3. That's going to give you 2. So 47 has a remainder of 2 when divided by 3. For 58 divided by 3 is going to be 19.3 bar. Again, I'm not interested in the 19, so I'm really just looking at that remainder of 0.3 bar. 0.3 bar times 3 is going to give you a remainder of 1. And actually, let me do that in the same colors that I did before to be consistent. So times 3 is going to be 1. So 47 has a remainder of 2. See how counterintuitive that is? 47 is a smaller number than 58, but it has a larger remainder. But 47 has a remainder of 2 when divided by 3. 58 has a remainder of 1 when divided by, excuse me, not 8. 47 has a remainder of 2 when divided by 3. And 58 has a remainder of 1 when divided by 3. So the sum of the remainders is going to be 2 plus 1. So your answer here should be 3. For number 2, Ryan's buying fruit at a local farmer's market that's priced at $3.65 per pound. If he has $19.71 on a gift card, what percentage of another pound can be purchased when he cannot purchase another whole pound of fruit? So we're going to take $19.71 and divide it by the price per pound of $3.65. And we're going to get 5.4. Notice that that means he can buy 5 whole pounds and 0.4 of another. But they asked you what percentage. So that's very tricky. If they ask you for a percentage, you need to make sure you give a percentage answer. So if you said 0.4, that would technically be wrong. That's not the answer. The answer has to be 40 because it has to be in terms of a percent, 40%. So I know that that sounds like it's splitting hairs, but that's a really common trick that they employ on this test. If they say percentage, you need to make sure that you've converted your decimal answer into a percentage by moving the decimal place 2 places to the right. If you don't, then you're going to get an incorrect answer. If you have any questions, please let me know. Otherwise, I'm going to give you 3 minutes. Please look at questions 3 and 4. Number 3 says, I'll give you some hints after the 3 minutes. Question 3 says, a company has internal accounting metrics that define a turnaround time, or in other words, that's the manufacturing time from start to finish, for product A to be 25 days. If the production schedule of product A starts on a Monday, then on what day of the week will the 4th subsequent turnaround schedule end? And question 4 says, Alexis is selling bags of sand, each weighing 7.6 pounds to a construction, I think that's supposed to say construction company. My apologies. If she has 2,300, I'm sorry, that should be 20, ooh. The decimal place messed up there. Let me just make sure that that works. Oh no, I'm sorry, there's a typo here. Let me just give me a few seconds to make sure that this problem works. Okay, there was an additional 3 here, so my apologies. This last 3 was a typo. So let me correct this. This should be 2,316.48 pounds. So I do apologize. That last 3, when I copied and pasted the problem over, didn't get cut out. So if she has 2,316.48 pounds of sand, and that is a decimal place there, how many pounds are left when she cannot make another whole bag? Okay, so I'll give you 3 minutes, and then I'll give you some hints. Okay, so for number 3, we have a turnaround period of 25 days. So if we investigate how many weeks that is, 25 divided by 7. So if we take 25 divided by 7 days in a week, that's going to give me 3.5714 blah, 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 blah. So I'm going to subtract away 3, because that represents 3 whole weeks, and concentrate on this remainder of 0.5714 continuing. So subtract away 3 and multiply by the divisor of 7. That's going to be a remainder of 4. So that means that every turnaround schedule, the last date is 4 days ahead of the start date. So for the first schedule, we started on a Monday. That means we're going to end on a Tuesday, Wednesday, Thursday, Friday. So we're going to end on a Friday, 4 days later. Well, it's 3 weeks and 4 days later, but if we go 1 full week, then we're ending on the same day that we started on. So the first schedule is going to start on a Monday, end on a Friday. The second schedule would start on that Friday and then end. If we go 4 days from Friday, we're going to go Saturday, Sunday, Monday, Tuesday. So it's going to end on a Tuesday. So on and so forth. Oops. What happened there? Sorry. So that's my hint for that problem. I'm going to give you a few extra minutes to work on that. Number 4, if she has 2,316.48 pounds and she's dividing that into bags each weighing 7.6 pounds, that's going to be 304.8. So how many pounds are left when she can't make another whole bag? So that means that she's able to make a total of 304 whole bags with a 0.8 remainder. Remember that you're going to multiply that 0.8 remainder by your initial divisor of 7.6 in order to calculate the total number of pounds that are remaining when she can't make another whole bag. I'll give you 2 more additional, that's redundant. I'll give you 2 more minutes to look over these problems, and then I'll give you the solutions. Okay, so for number 3, I filled in a few other, for the third schedule. Notice that the second schedule turnaround schedule ended on a Tuesday, so we're going to start the third schedule on a Tuesday. That means it's going to go 3 weeks and 4 more days. So from Tuesday, we're going to go Wednesday, Thursday, Friday, Saturday. So the third turnaround schedule is going to end on a Saturday. That means the fourth schedule is going to start on the Saturday, go 3 weeks and 4 days more. So then we're going to be from Saturday, Sunday, Monday, Tuesday, Wednesday. So that's going to end, our answer here is going to be Wednesday. And for number 4, if we subtract away the 304 complete bags of sand that she can make, we're left with a remainder of 0.8. If we take 0.8, which is the percentage remainder, or the decimal version of the percentage remainder representing 80% of another whole bag, if we take 80% of another 7.6 pounds, we're going to get 6.08 pounds remaining when she cannot make another whole bag. If you have any questions on anything that we've done today, then please let me know. Otherwise, I'm going to end our session today here, and I'll pick back up in the second session that I'll make a recording of, so look out for that. Those will be posted as soon as possible, and then we'll end this section on Friday with session 3. But if you have any questions, then please let me know. Otherwise, thank you very much for watching. Dr. Tot, would you like to say goodbye? Come on, you guys say goodbye to everybody. You say bye? Very good. Thank you guys very much for watching. Look out for the recording for session 2, and then I'll talk to you all either on tomorrow, Thursday, for our writing skills session, or on Friday for session 3 of the mathematics. So have a wonderful night. I'll talk to you all Thursday or Friday.